A few videos ago, we introduced some of the fundamental ideas or problems that calculus attempts to solve. And in fact, it's not just an attempt. Calculus is what we need to solve these problems. And today, we will actually see how, with the aid of a limit, we will be able to tackle one of those problems. And let me just do a quick reminder of what that problem is. So let's say we have a function that's nice and continuous, and it doesn't have any even sharp corners. So let's say we have a nice smooth graph that looks like this: y equals f of x. And then we're going to pick a point on this graph. Let's say we pick, let's start over here. Let's say we pick this, and I'm going to call it x0, or I could have called it a. And what we would like is, we would like to be able to find the line that passes through the same point here, but just kind of kisses or just glances along the curve. So this line that looks like this, right? We would like to be able to find its equation. And all we are given is the equation for the curve, right? And the x value. Now, once we know the x value, we can find the corresponding y value. So let's call that y0, right? So basically, we know a single point that this blue line passes through, and the fact that it just kind of glances or just touches the curve at that specific point, right? This sort of line is called a tangent line, right? So it's called a tangent line. And since we already know the point that it passes through, if I wanted to find the equation of this line, think about what I need if I have to find the equation of a line. I need at least one point that it passes through, and I need to know its slope, right? So that's one of the fundamental questions of calculus. Given a function like this, and we define a tangent line this way, and we'll be a little bit more precise shortly, right? In fact, it's because of our need to be precise why we're going to end up using a limit. But again, given your function and a point on the function, and this sort of line that just touches the graph at that particular point, the question is, what is its slope, right? So the tangent line, the question is, what is its slope, right? And you might say, well, why do I even really care? Well, trust me, you will care. When we figure out how to answer this question, suddenly a whole entire world opens up in terms of other types of questions that are related to this concept, but are far more, you might say, interesting or useful than just finding the equation of this line or finding its slope, right? And just to give you an idea of, in fact, another reason why this question is fairly interesting, what if we had different points? What if we picked different points? What if we had another x value? Let's say call that x1. And I'll just do a couple more. Let's say we have this as x2, and then let's say we have this as x3. So what if we have different points here, and the same question is, what if I just drew a single graph, a linear function that just touches the graph of y equals f of x at one point? So I won't extend this tangent line too much, but what about the line that does something like that, right? Or what about the line that does something like that? Or what about the line, and this one I will do like this, like that line. So notice all of these, the blue, the green, the red, and this white line, these are all tangent lines. And if you notice, just looking at them, it looks like they all have different slopes. You know, that they all look like they have different slopes. So depending on where I put this specific point, I'll end up with a different slope and therefore a different line, right? And the question is, we want to be able to find the slope of each of those colored lines and the white line as well, right? And again, the only thing we're going to be given would be like the graph of or the equation, let's say, of our function and an x value, right? That's the bare minimum. Sometimes we might be given the ordered pair, but at the very least, we'll have the x value and the equation of the curve, right? So let's see if we can build the idea behind the solution to this. And the starting point for the solution goes back to algebra. And it goes back to the concept of an average rate of change. So I'm going to draw another function. And this time, so let's say it looks like this. I am going to pick 2 points on this function, the graph of this function. So, and I'm going to label it, let's just label them for simplicity. Let's label this point A, and then let's say we have a point over here, let's call it B, right? And then immediately I know the y value. So the y value that corresponds to this x is f of A, and the y value that corresponds to this x would be f of B, right? So we got f of B. Now from algebra, we have this concept of average rate of change. So for instance, if you look at the graph of the function, part of it here, it's like going up, and then it kind of plateaus, and then it goes back down, and it plateaus again somewhere around here, and then it goes back up. So as x changes from this number to this number, right? So from x equals a to x equals b, you can see how the y value changes. That's part of the information that's given in your graph, right? So if we wanted to know, like on average, at what rate does the function change or the y value change as x changes from x equals a to x equals b, what we do is we use the slope of the line that connects these 2 points. So I connect these 2 points with a line. Let me extend it a little further, right? And if we look at the slope of the line, that gives me on average the rate at which the function value changes as x changes from a to b, right? And this line that passes through 2 points on the curve, it doesn't like just glance it at one particular point, but it literally passes through 2 points on the graph of our function. This sort of line is called the secant line, right? And its slope, now we typically use m for slope, so I'm going to use m, and then since this is a special line, I'm going to use a subscript, and that subscript will be the abbreviation SEC. So we're going to use the abbreviation SEC for secant. Now, since I know 2 points that the line passes through, then I can use my basic slope formula, which is rise over run. Let me just introduce some other notation here. So, the rise is going to be the change in the y value. So in this case, you notice your y value starts down here, and then it increases and it goes up to here, right? On average. So this difference right here is the rise. And there are lots of ways you can write it. It's literally f of b minus f of a, right? And Since this difference also can be interpreted as a change, it's often represented as the change in the y value, so like delta y. So delta, uppercase delta, is typically used in math whenever you want to indicate a certain change, right? And then what is the run? Well, the run is that distance, right? And so this would be our run. And from an equation standpoint, if I just want to find this distance, or formula standpoint, it's just b minus a. So it's b minus a. And this is a change in the x value as x changes from a to b. So we can still use the delta notation, but we now say that it's delta x, right? So there are lots of ways we can write this down. So first, again, here is the concept, rise over run, because the slope of that line, that red line, is constant, right? So rise over run. Symbolically, we can represent it as delta y over delta x. And then as an actual formula now, it's the f of b minus f of a over b minus a, right? So all of these are saying the exact same thing. This is the slope of the secant line. And the number that we end up with, right? And remember, slope is going to be a number. In this case, a constant slope. We define this, we call it the average rate of change, right? So the average rate of change of my function, so of f of x, over the interval a to b, right? So the average rate of change of f of x over the interval x going from a to b, right? And you might remember this sort of calculation or this concept from algebra. Right? So let's do just a quick example of this to show you what the calculation looks like. And then what we're going to do is use this concept to solve our desired problem, which is the tangent line problem, right? And there is a nice relationship between these, right? But let's do a quick example of this first. And again, I'll take a simple function, not to really make things complicated. But let's say we have a parabola, like x squared minus 3x plus 4. And let's say the interval is from -1, let's say, to 3, right? And the nice thing with a lot of the formulas that we will encounter is you can apply the formulas without knowing precisely what the graph of the function looks like, right? So I'm not going to sketch this parabola. We should all be able to sketch a parabola, but let's compute the slope of the secant line that passes through the 2 points on this curve, with one point being x equals -1 and the other point being x equals 3, right? So we need so the slope of our secant line, again, that is our delta y over delta x. That's kind of the symbol for it. Either symbol, you don't have to use both, but again, I'm using both for emphasis. But what it is, it's the f value, the function value evaluated at the larger endpoint minus the function evaluated at the smaller endpoint, and then this is divided by the difference between the x values, right? And again, if you remember your basic slope formula, y1 minus y2 over x1 minus x2, or something to that degree, well, your function values are just your y values. So that's your y1, and this is the other y, this is your y2, and then this is the corresponding x1, and then the corresponding x2. So let's evaluate f of 3. So take 3, plug it into our parabola. What do we have? So we have 9 minus 9 plus 4. And then minus, let's repeat that process with a different x value. This x value being negative 1. So negative 1 squared, so we got 1. And then negative 3 times negative 1, that's a positive 3. And then plus 4, right? So that's the numerator. And in the denominator, we have 3 minus negative 1, that's 4. So now let's see what simplifies. Well, definitely the 9's cancel out. And so in the first pair of parentheses, we have a 4. And then minus, let's see, the second pair of parentheses, we have an 8. And then this would be divided by 4. So our final answer is negative 4 divided by 4. That's negative 1, right? And this is what we define as the average rate of change of this function over the interval negative 1 to 3, right? And actually, since it's a rate, it technically would have units, but we don't know what the units of y or the units of x are. But this is what we could say. We can actually write the generic units. It's negative 1, and it would be units of y, so whatever units of your numerator, so it would be units of y, and then per unit of x, because we're dividing by x, right, or a change in x, so this would be per unit of x. So it might end up being something like miles per hour, or gallons per minute, or air, just any quantity that you can think about, and then any variable that might affect that quantity. Those could be your units right here, right? But as you can see, this calculation is purely algebraic. Function evaluations, differences, and then a division or a quotient, right? In fact, this delta y over delta x is actually referred to as a difference quotient, right? More precisely, it's actually a quotient, right, which is just a fancy word for a fraction. It's a quotient of differences because there are two differences that you're computing, one for the rise, one for the run. So let's just actually write that down. So delta y over delta x is sometimes referred to as a difference quotient. All right, and again, we'll use this phrase several times, and we're referring to something like this in that instance. All right. Okay, so now let's see how we could possibly take this idea and now find the slope of a tangent line. Right. So again, let's start with another graph. Now, what I'm going to do with this one is I'm going to draw, here's my function, y equals f of x. And let's say I want the tangent line at this point. And I'm going to call this point A. So this is fixed, right? And I want the tangent line there. Let me sketch the tangent line like I did earlier. I'll sketch this in blue. Right? And what we want is this slope, right? What we can do is I'm going to start out with a secant line, and I'm going to describe a process by which the secant line magically turns into the tangent line. And who doesn't like magic? And this is how it works. Now, for the secant line, I need another point somewhere. So what I'm going to do is pick a point, let's say right here. But this point is not going to be like the fixed b that we just used in our example. This point is actually going to be a variable because I'm going to make this change almost like I have a slider there that'll be sliding the x value along the x-axis. And as I slide the x value here, it will affect the point, right? So as it is, obviously I'm drawing things in a static way, but let's draw the secant line that connects these 2 points, right? So it's going to look something like this, right? And then let's do the same thing and compute its the slope of the secant line of this one. So let me write this down again. The only difference between what we just did and what we're doing now is I'm saying that this larger x value is not constant anymore, right? So that's where we're using a letter, the letter x, which indicates our independent variable. But we can still write down the slope of this. It's f of, now not b anymore, but f of x minus f of a. I almost wrote f of x. So f of x minus f of a, and then divided by x minus a. This is still our rise over run. This is still our delta y over delta x. Still our difference quotient, right? Now what I'm going to do, I am going to simulate, and I'll do this in sequence so you can see what's happening. I am going to simulate what will happen if I now made this x value get closer and closer to this fixed x value. So this one is not going to change because this is where I want my tangent line to be, right at that point. So what I'm going to do, almost like a slider, I'm going to slide the x value to the left, right? And by doing that, right, I will have different points on the graph. So if my x value is right here, this would be the point on the graph. If I slide it closer here, it will be over here. So I'm just going to do a few of them, right? And maybe I'll do one more there. And now with these other points on the graph, let's repeat the process of drawing the secant lines. But now it's not just going to be one, it's going to be many. And I'll draw these dotted. So let's connect these 2 points right here. See if we can get the slope to be pretty good. All right, so there's one more. And then now let's connect these 2. Like that. Then let's connect these 2. So like that. And then let's connect these 2 that look like this, right? And what happens is, if you notice, so we have, it's almost like we have a set of secant lines now. And the closer and closer x, my variable, gets to this fixed constant, the closer and closer the red secant lines are getting to the blue tangent lines. So if I wanted to find the slope of the tangent line, what I would have to do is let x approach a and make x as close to a as possible, right? So let's write that down, and then we'll give you the notation. So to find the slope of the tangent line in blue, so the tangent, and here is the notation for the slope of tangent. So I'm still going to use m, but I'm not going to use this SEC subscript. I'm going to use TAN for tangent. So to find the slope of the tangent, we let this x value get closer and closer to this fixed number, and we see what happens to this difference quotient. So we let x approach a and see what happens to our difference quotient, right? So, and I'll say see what happens to delta y over delta x as x approaches a, right? So let's write that down symbolically. Now, what operation did we have? We just studied quite a bit of where we're letting things get very, very, very close to fixed numbers, for instance, right? That sounds a lot like a limit, and that's precisely what is needed here, right? So the slope of the tangent line, so let's write that down. So m sub tan, it's like you start out with a regular difference quotient, but then what you let happen is you let your x variable get closer and closer to a, and that is a limit. So basically all I have to do is put my limit notation, my limit operator in front of this difference quotient, and if that limit exists, right, and we know that sometimes limits don't, but if that limit exists, it is defined as the slope of our tangent line. So let's write that up. So if we put, right, and again, this is our symbol for letting x get closer and closer and closer to a. And the reason why we're doing the two-sided limit is I drew it as x being on this side of the constant a, but it could also be over here. It could also be on the left side. So we're going for the two-sided limit because we know how important that limit is. And then we're taking the limit of this difference quotient, right? And there we go. So this is the slope of the tangent line provided the limit exists, right? So provided the limit exists. All right. So, and that's again a big conceptual leap. As I said, just finding the slope of a secant line, that's an algebra question. Now, finding the slope of a tangent line, because it involves a limit, and that's considered our calculus problem, right? So let's look at an example of this. And just like the example we did earlier with the parabola, let's also use a parabola and see what's going on, right? So let's do an example here. And now, this time I will sketch the parabola. So let's say f of x is equal to x squared minus 4x plus 3. So let's say this is our parabola. And now the difference is we're just going to have a single x value. So let's say x is equal to 1, right? So let's kind of sketch this and see what it is we're trying to do. Now, in terms of sketching this parabola, there are lots of ways you can do it. If you notice, this parabola, it factors, I'll do the factoring above. So it factors as x minus 3 and then x minus 1. So it has roots at positive 1 and positive 3. And we know it has to open up. So we have a pretty good idea of the general shape of this parabola, right? And also looking at it, we could see that it has a y-intercept of 3. So lots of information we can get pretty quickly. And so here is one root, here is another root, and let's say this is 1, 2, 3. So the parabola will look something like this. right? So that's the graph of f of x. And what we're looking for is the slope of the tangent at x equals 1. So I picked x equals 1 because it's right where it has a 0. So it's right where it touches the x-axis right here. And let me sketch what the tangent line would look like. And I've been doing the tangent lines in blue, so let's do this in blue. So we're looking for the slope of that line, right? And in fact, once we find the slope of this line, we'll actually go ahead and find the equation. So we will do two things here, right? So this problem is set up exactly for us so that we can use now this limit definition of the slope of a tangent line, right? In other words, this is a definition, provided the limit exists, right? So let's set this thing up. So in this particular example, a is equal to 1, right? So the slope of the tangent to this parabola at this specific point is determined by this limit. So it's going to be the limit as x approaches 1, because that's my constant value right here, right? In fact, let me label it just so you can see this is the a value, right here. And then let's set up our difference quotient, and I'll set it up symbolically, right? So it's f of x minus f of 1 all divided by x minus 1. And we know the function, so we're going to put our x squared minus 4x plus 3 right here. We can figure out the y value from this, and then we're going to simplify this, and then this is where all our techniques from limits kick in. We're going to have to figure out how to evaluate this limit. So when I plug f of x right there, it will be the expression x squared minus 4x plus 3. Then when I plug f of 1 in, that's going to be a number, and it's 1 squared minus 4 times 1 plus 3. So that's the entire numerator, and then it's all over the quantity x minus 1. All right? So definitely we can simplify the numerator quite a bit, right? So let's see this. So we have an x squared, we have a minus 4x, we have a plus 3. Let's see how this second pair of square brackets simplifies. Well, let's see. We have, so now if you think about it, right here we are evaluating the function at 1. But we know that the function value at 1 is 0 because it has a root right there. And if you look closely at this calculation, it is 0. You have 1 minus 4 and then plus 3, so that's equal to 0. So this constant right here completely cancels out, and what I have is just x minus 1 in the denominator. Now let's try to use our limit properties. So let's try to take the limit of the top. Well, if I try to take the limit of the top, again, if I plug 1 into this polynomial, I'll get 0 because I'll have 1 minus 4 plus 3, that's equal to 0. And if I take the limit of the bottom of x minus 1, that's also 0. It's 1 minus 1. That's also 0. So it turns out this is one of our indeterminate forms. Does it mean that we stop? No, it means we don't know. The 0 over 0 doesn't mean anything. Like writing indeterminate as an answer is basically saying, I don't know. Well, how do we know? What can we do to make our answer well defined? Well, in this particular case, we can factor and reduce. And we know how the function factors. We still have it right here in blue. This is the factorization of that quadratic. So it looks like this. So it factors as the x minus 3, x minus 1, and lo and behold, right? Our factor theorem tells us if we plug 1 in and we get 0, then x minus 1 has to be a factor. That's a very important theorem from algebra. So we can reduce this, right? And then we end up with a much simpler limit to evaluate. We try to plug in the 1 again, and this time we will definitely get a number, and the slope is 1 minus 3, which is negative 2. And that is somewhat consistent with our graph right here, right? We can see that at the very least, the tangent line is sloping downwards, so it should have a negative slope. Now, the fact that it comes out to be negative 2, that's all in the details of our calculation. But at least we can see that the negative sign is consistent with what our graph is showing us, right? And this is the slope of that tangent line. What if I wanted to find the actual equation, right? The actual equation of the tangent line, right? So there is its slope. Here's the follow-up question. What is the equation of the tangent line at that point? So of the tangent at x equals 1. Well, now that we know its slope, right, we know the point that it passes through. It's the point 1 comma 0, because that was one of the roots of the polynomial, right? So the tangent passes through the point 1 comma 0 with slope negative 2. So now think about how you find the equation of a line, right? There's several formulas you can use. You can use your y equals mx plus b, because we have a point, we have the slope, and we can use that equation to find the y-intercept. Otherwise, we can use the point slope form, and that's the form I will use. So this is the point slope form of the equation of a line, and this is the general formula: y minus the y value equals, now specifically it's going to be the slope of the tangent times the quantity x minus the x value. So this hopefully is one of the equations that you've seen before for the equation of a line. And then let's plug the three numbers that we have, right? What are those three numbers? Well, the y value is 0, the slope is negative 2, the x value is 1. And then what we're going to be left with is an equation, but it's going to be a linear equation that gives me the all the points on the tangent line. So let's simplify. So we have y minus 0 is equal to negative 2 times the quantity x minus 1. And if so, y minus 0 is y. Distribute the negative 2, and then we get that the equation of the tangent line is now negative 2x and then plus 2, right? So what we just found, right, after doing the calculus that involves the limit, finding the actual equation of the tangent line, again, it reduces to an algebra problem. So I'm going to scroll back up to the graph that we drew. And now what we can say, we can add a lot more detail to this, right? So there's the function, that's the parabola. And what I can now say is that the equation of the tangent line is y equals negative 2x plus 2, right? And there you go. So we're now able to find the slope of the tangent to a given curve using this limit definition, right? And in subsequent videos, we're going to look at alternatives to this and then work our way to a really, really big concept in your first semester of calculus. So why not watch the next video and see what's coming up next? See you then.